Let's start our seminar. It is my pleasure to announce the speaker. This is a Professor Leonard Susskind. He will tell us about the sitter choreography. Please, Lenny, 1 hour.
Okay.
Please share your screen.
You'll just stop me when an hour is up. I don't know how much material I have, but
approximately.
Okay. Just sharing my screen now, so hold on a second. Stop.
People are still coming.
Can everybody see my screen?
Yes.
Yeah.
Okay, good. Tell me when. You won't be able to see me. My iPad won't support you being able to see me. At least I don't think you can see me.
Just one small technical thing.
I can't see you. Hmm?
One small technical thing. If will be some strange people around, I will, as a host, mute everyone. But you, as a speaker, you a co-host, you can immediately unmute yourself and continue talking. So it's just to people who want to ask questions. If there will be some unneeded noise, I will forcefully mute everyone, and then you will have to raise a hand.
But I would like somebody to be unmuted so that while we're proceeding, I can check and make sure that I'm still connected with you, because I've had it happen more than once in the past.
No. We hope people will behave appropriately, but sometimes some strange people around.
Right. But somebody should stay on so that I can check and make sure that we're still connected.
Yes, sure.
Good. All right. You tell me when you're ready.
Actually, we are.
Okay. Good morning or good evening. It's very early in the morning here. I just woke up, and this business of the Earth being round, we have to do something about that. It's causing problems. For example, you are at 7 o'clock or 6 o'clock wide awake. I'm at 8 o'clock in the morning and still half asleep. I hope in the next 10 minutes I'll wake up. And I'll wake up enough to give a decent seminar, but let's just proceed. Good. All right. So the sitter space. The sitter space, in some respects, is the elephant in the room. Does everybody know you don't have to answer me, but I'll ask anyway. Does everybody know the expression elephant in the room? The elephant in the room is a thing which, well, maybe it's a thing you don't notice just because it is so big and has always been there. Or you may be a little bit afraid of it. It's so big that you're afraid of it, or for one reason or another, you ignore it. The elephant in the room of theoretical physics, and in particular, the area of theoretical physics that I'm interested in, quantum mechanics and gravity and their connection, the elephant in the room is de Sitter space. Now, I think people are starting to wake up to the elephant, but up till now, almost everything that we've managed to learn, and that's a lot, about quantum mechanics and gravity has come either from flat space or more recently means the last 20 years, from anti-de Sitter space. And I think it's true that we're sort of gradually beginning to wake up to de Sitter space. Why should we wake up to de Sitter space? Well, because we live in something that's much more like de Sitter space than anti-de Sitter space. Now, there's another parable about elephants. Maybe you know it. It's the parable of the 5 blind men who are asked by the king to feel the elephant and tell us what it is. They're all blind. They can't see the whole thing. They each feel the part that they are close to, and they come to radically different conclusions. One says it's DSCFT. The other says it's DSDS. Another says it's T-bar T. It's the swampland. It's matrix theory. And nobody sees the whole thing. And I think that's very, very true at the present time with respect to de Sitter space. Lots of different ideas. Some of the ideas are good, some of them will go away. It's impossible to tell right now which are which. And so giving a seminar on de Sitter space is a little bit difficult because we don't really know what's right in the quantum mechanics of de Sitter space. What's more, we don't even know if de Sitter space can exist. By de Sitter space, I will always mean, for the purpose of this lecture, eternal de Sitter space. De Sitter space that lasts forever and ever. We don't know that it can exist, and we don't know, even if it does exist, what the principles are. My approach to it is, I would call it phenomenological, except that the phenomena we're talking about are not experimental phenomena. What I would substitute for, in trying to understand the quantum mechanical degrees of freedom, the holographic degrees of freedom of de Sitter space, I'm inclined to use gravity calculations as a source of data to be interpreted by quantum mechanical, to be interpreted quantum mechanically and holographically. So I will describe today some circumstantial evidence. This is a very bottom-up kind of seminar, not top-down, not starting with some fundamental principles and deriving things, but starting with some empirical observations coming from gravity and attempting to learn something about the quantum mechanical degrees of freedom. Is everybody still there? Hello, are you there?
Yes, yes.
Oh,
Yes,
okay,
yes,
you
yes.
got to answer me because, as I said, I'm somewhat insecure about being disconnected. All right, so what we're going to talk about is a form of de Sitter space holography, which I call static patch holography. Static patch holography, I'm going to assume you've seen the Penrose diagram of de Sitter space. On the left-hand edge here, the left-hand edge is not like the left-hand edge of anti-de Sitter space. It's a point. And on the right-hand side here is also a point. And I've taken to calling these points, some people call them the poles, the North Pole and the South Pole. I call them the antipode and the pode. Pode is not a word apparently in the dictionary, but antipode is the opposite end of a sphere. This is what the Penrose diagram of de Sitter space looks like. I'll assume you know it. I'm not going to explain it. On the right part of the diagram over here, we have a spatial slice through the center of de Sitter, through the t=0 surface of de Sitter space. And what is it? It's a sphere in whatever number of dimensions we're in. But I'm inclined to stay in 4 dimensions, and I will stay in 4 dimensions. The pode is a point at one end. The antipode is a pode at the other end. The horizon, now there are 2 of them. They intersect at this point. So strictly speaking, I should draw these 2 horizons touching each other if I'm really quite at t=0. But if I displace my surface a little bit, here's a surface, let's displace it a little bit, then we see that the horizons are separated from each other, and that's what this picture is over here. Okay, so this is a spatial slice. Here is the metric of de Sitter space. Again, I will assume you're familiar with it. And another thing I will assume you're familiar with is the thermodynamics of de Sitter space. Now, I should have said right here that the static patch of de Sitter space is a piece of de Sitter space. Here is a static patch. The static patch has a metric which is static. In other words, time independent. And it's a good place for formulating a set of quantum mechanical principles based on a time-independent Hamiltonian version of quantum mechanics. The static patch is in thermal equilibrium. First of all, it's static. Second of all, it's in thermal equilibrium. It has a temperature, which is 1/2 pi r, where r is the radius of the de Sitter space. It has an entropy, which I'll call S0. The naught here just indicates that I'm talking about empty de Sitter space. And its entropy is pi divided by g by r squared times r squared. This is This is actually 4 times the area of the horizon divided by G. And there are some hidden assumptions in saying these things. Entropy and thermodynamics and so forth only really have, the only basis for them is unitary quantum mechanics. The second law of thermodynamics, for example, is fundamentally based on the assumption of unitarity, the rules of quantum mechanics. And so there's some hidden assumptions that there's a unitary quantum mechanics of the static patch, that there's a Hilbert space of states, that there's a Hamiltonian if we want to define temperature and energy, particular temperature. Also, that there's a symmetry, which I won't get into today. It's the symmetry which takes us from one static patch, rotates the de Sitter space, and moves the position of the pole and the antipode. I won't get into that today, but it's an important part of the story. All right, now we're interested in the holographic principle. The holographic principle tells us we should seek a description of the quantum mechanics on a one less dimensional surface, which we can call a screen. Where shall we place that screen? In anti-de Sitter space, the screen is placed out near the boundary of the anti-de Sitter space. In de Sitter space, exactly the opposite or something very, very different is true. If you look at the Penrose diagram, where is it? You might be tempted to think of the pode and the antipode as being like the boundaries of the de Sitter space, but they're not boundaries, they're simple points. And you might be tempted to think that you can place the degrees of freedom of the hologram out near the pode, but there's not much area there.
There is some question here in the chat.
Yes.
Do you mind to answer it maybe?
No, go ahead.
It's from Robert Brandenberger. Robert, maybe you will ask yourself.
Okay, so a key assumption is that the static patch is in thermal equilibrium. And so how do you justify this?
Oh, well, come on. This is 50 years of physics. I'm not going to justify it. We're going to assume it. We're going to assume the last 50 years of gravity. Hawking will explain it when he lectures next time. Okay, sorry about that. All right. So where do we place the holographic screen, so to speak? If we place it sort of surrounding the pode over here, it doesn't have much area. If it doesn't have much area, it certainly doesn't have enough degrees of freedom to describe the entire static patch. Based on covariant entropy bounds, the place to put it is at the horizon. Why? Because it's only the horizon that has enough area to encompass all of the degrees of freedom in the static patch. Again, I will not try to derive that. And so it's natural in static patch holography to imagine that the degrees of freedom are at the, let's call it the stretched horizon of the static patch. In other words, they surround us on a surface which we ordinarily think of as the cosmic horizon. All right, what I'm going to talk about today, we'll see how far I get. I'm going to talk about, in fact, in some sense, this is the main lesson of my seminar today, but let's go a little further. Evidence, circumstantial evidence that in 4 dimensions, strictly in 4 dimensions, that the fundamental degrees of freedom of de Sitter space, the holographic degrees of freedom, include matrix degrees of freedom. Matrix degrees of freedom in roughly the same sense as in matrix theory. So I will explain why, but before I explain why, let me explain the kind of probe that I think is useful in this context. The probe is the study of fluctuations away from thermal equilibrium. Now, fluctuations away from thermal equilibrium are a funny idea. We're talking about thermal equilibrium, but even in thermal equilibrium, fluctuations happen, and the fluctuations can take you far from what you thought naive equilibrium was. For example, the famous example is the gas in the room. In thermal equilibrium, from time to time, very rarely, all of the gas in the room can accumulate on one side of the room, or even in the small corner of the room. That's a part of thermal equilibrium, but it's also a fluctuation far from what we naively think of as thermal equilibrium, which is the room being filled uniformly with gas. The same thing is true in any thermal system. There are Boltzmann fluctuations. I use the term Boltzmann fluctuations because Boltzmann was very concerned with these kind of things. Large-scale fluctuations, extremely unlikely. And the formula for the probability in this picture here, what I'm imagining is a fluctuation in which a large number of degrees of freedom, particles, let's call them, accumulate near the pole, and a large number on the other side near the antipode. It is a fluctuation. It's very unlikely. And the probability for it is e to the minus the entropy deficit. So let me explain what the entropy deficit is. The entropy of de Sitter space is just S naught. Let's write it down. S naught. The constrained entropy, the entropy of the system subject to the constraint that the fluctuation has happened, that's smaller. Why? Because we put some constraints on the system. Whenever you constrain the system, the entropy, the number of states that satisfy that constraint is smaller than the number of states that you started with. And so the entropy is smaller. And that is what I will call the entropy deficit. The entropy, the difference between the entropy of the thermal equilibrium and the state with the fluctuation, and that's the probability. These probabilities are, and study of them are a useful probe. This is about all that happens in thermal equilibrium, fluctuations. And the study of these fluctuations is a good probe of microscopic degrees of freedom. Good. Okay, so let's move on now from de Sitter space, and we're going to study these fluctuations, but from de Sitter space to de Sitter Schwarzschild. What I'm thinking about now are fluctuations in which enough degrees of freedom accumulate near the pole here to define a black hole or to form a black hole. If a black hole forms, the black hole itself has a horizon, and the problem becomes more complicated. Here is the metric for Schwarzschild de Sitter. It has the same term in the emblackening factor as the Sitter had, but it also has a term which you'll recognize as the Schwarzschild term. Okay, horizons. Where are the horizons? Where is the horizon, or where are the horizons? The horizons are at the root, meaning the zero, of f of r. They're defined by f of r equals 0. And if you stare at this function a little bit, in particular, if you multiply it by r, you'll notice it's a cubic polynomial. We're gonna come back to it. It has 3 roots. One of them has a negative value of r, has no particular meaning. 2 of them have positive r and define proper horizons. What are those 2 horizons? One of them is the cosmic horizon, and the other is the black hole horizon. I'm going to begin with what I'll call small black holes. Small black holes are black holes whose Schwarzschild radius is much, much smaller than the radius of the de Sitter space. Another way to say it is that the entropy of the black hole, which I'll call small script s, this is the entropy of the black hole, is much, much less than the entropy of the cosmic horizon. So we're studying small black holes nucleated by fluctuation in a de Sitter space. Here's the Penrose diagram. If you're not comfortable with Penrose diagrams, you can ignore it. But here is the Penrose diagram for de Sitter space with a Schwarzschild black hole in it. We're going to see in a moment that it's really 2 Schwarzschild black holes. I think I won't describe this too much. If you've seen it, you've seen it. The main important point is that it's periodic. This boundary over here, this dotted boundary over here, gets identified with the boundary on the other side, so it forms a cylinder. R plus in here is the inflating region of de Sitter space. Here is the singularity of the black hole. If you fall in here, you hit the singularity. If you fall out here, you enter into exponentially expanding space. And an observer who stays out here is in the static patch. Here's one static patch. Here's the opposite static patch on the opposite side here. Okay, what does this look like? A slice through t equals 0. Well, it looks like the original de Sitter space, except it has a black hole. Here's the black hole at the pole. It also has a horizon over here. That horizon is small. Here are the horizons of the two static patches as they would be without the black holes. And here at the other end, at the antipode, is another black hole. And these two black holes are identified, which means they have an Einstein-Rosen bridge connecting them, and those black holes are therefore entangled. Incidentally, the two horizons, they're over here, one over here and one over here. Those two horizons are also entangled. And I'm using standard wisdom now. I'm not using anything new, but I'm not going to justify it. The left side and the right side are entangled in two ways. First of all, the cosmic horizons on the two sides are entangled, and the black holes are entangled. Okay, what is the probability that such a fluctuation takes place in which a pair of black holes like that spontaneously appears in the thermal equilibrium configuration? And the answer is the probability is e to the minus the entropy deficit. The entropy deficit being the entropy of pure de Sitter space minus the total entropy associated with the state, including the black holes. The entropy of the state, including the black holes, is the sum of the area of the cosmic horizon plus the black hole horizon. And we can calculate it. We can calculate it from, where do we get it from? Let me go back a step. We get it from the metric. Here's the metric. We solve for the horizons. I'm not going to do it. I'll tell you the answers. We solve for the position of the horizons. We plug back in. We calculate the area of the horizons. And we take the difference between the full de Sitter entropy and the sum of the areas of the cosmic horizon and the black hole horizon. That's an easy calculation. It's easy if we're doing this to lowest order in the mass of the black hole. The black hole is assumed to be much, much smaller than de Sitter space. Oh, here's the formula. It's pi over g times capital R squared. That's the de Sitter entropy. And then we subtract off the entropy of the cosmic horizon and the entropy of the black hole. And we get an answer. The answer is 2 pi times the Schwartz times the cosmic horizon, times the length scale of the de Sitter space times the mass of the black hole. This you may recognize. If not, I won't bother. It's a well-known expression. I'm not going to delve into it, but it can be re-expressed. The mass of the black hole is proportional to the square root of its entropy. The radius of the cosmic horizon is proportional to the square root of the cosmic entropy. And if we plug in carefully, we will find out that this expression is just the square root of the cosmic horizon entropy times the black hole entropy. This is leading order in small s, in other words, for small black holes. This is a purely information theoretic quantity. There's no place in it is there any reference in detail to gravity. It's simply an information theoretic quantity associated with the entropies of the black hole in de Sitter space. And the question is, what kind of hint, what kind of clue as to the fundamental degrees of freedom might be in this formula? Okay, so I will tell you what the clue is, or what it seems most likely the clue is. The clue appears to suggest that the de Sitter space degrees of freedom are matrix degrees of freedom. Matrix degrees of freedom in the same sense as BFSS matrix theory. This was first noticed by Banks, Fiol, Morrissey, and in around 2006. Around the same time I noticed it, but I didn't publish it till 2011. But I'm going to tell you now, what's the connection between this peculiar formula? This formula is peculiar. It's not something that would be expected in any other statistical system that I know of. And so what kind of degrees of freedom would have a formula like that? And the answer is matrix degrees of freedom. So let's assume that the fundamental degrees of freedom of de Sitter space have the form of matrices, n by n matrices, in the same sense that of course, this is also true. This is also true in ADS. The matrices then are just the matrices of Yang-Mills theory, the matrix degrees of freedom of Yang-Mills theory. It's also true in matrix theory. It's not a surprise that degrees of freedom would be matrices, but not matrix field theories like Yang-Mills theory, but just matrices, some finite set of matrices. That's the assumption. Let's start with that. We start with that system. There are n squared degrees of freedom, and let's start with thermal equilibrium. Whatever the Hamiltonian is, I don't know what the Hamiltonian is, but there are n squared degrees of freedom, and we can therefore assume that the entropy is proportional to n squared. Sigma simply means the entropy per degree of freedom. I'm not going to tell you what it is because I don't know, but I assume it's a number of order 1. That seems innocuous. That seems nothing unusual. So let's start with that. But now, how do we describe a configuration in which a fluctuation has happened and the degrees of freedom have separated into a subset of the cosmic horizon and the subset associated with the black hole or associated with the fluctuation? Well, I'm going to take my inspiration from matrix theory, from BFSS matrix theory. It is also something that one sees in Yang-Mills theory. And I'm going to say that the two sets of degrees of freedom correspond to blocks. Block diagonal matrices, the larger block being associated with the cosmic horizon, the smaller block in this case being associated with the fluctuation, the smaller fluctuation, and again motivated by matrix theory, that it is a configuration in which the remaining off-diagonal degrees of freedom that belong to neither of these are stuck in their ground state, are unexcited completely. So I'll just call those 0. What would the entropy of such a configuration be? Well, how many degrees of freedom are excited? All the degrees of freedom of the cosmic horizon, all the degrees of freedom of the black hole, and none of these off-diagonal elements. You can think, if you like, of the off-diagonal elements as strings connecting the black hole to the horizon. And we're basically assuming there are none there. Okay, so let's see if we can now calculate the entropy deficit. The the thermal equilibrium entropy is sigma times n squared. The entropy of the new state, the constrained state, first of all, has a term coming. This S here is the cosmic horizon. It's the entropy of this block. This block, how big is it? It's n minus m times n minus m. So it has n minus m squared degrees of freedom. This block has m squared degrees of freedom, little m, whatever little m is. And if we add it all up and subtract s naught minus s minus little s, what we will get is twice sigma, sigma occurs everywhere, times n times m with a factor of 2. Let's not worry about the factor of 2. Another way to think about this delta S is it's just the number of constraints, the number of degrees of freedom that have been constrained to be in their ground state. And how many are there? N minus m, that's this, times this, m. So that's the number of constraints. It's the entropy of a state, the conditional entropy of a state conditioned on the fluctuation being present, with the other degrees of freedom being set to 0. And what is it? Well, we can work it out in terms of the entropies. Oh, incidentally, we're working to lowest order in little m. And to lowest order in little m, it's simply the square root of big N times the square root of little m, which is the square root of the cosmic entropy times the black hole entropy. Exactly the formula that general relativity gave us, the general relativity calculation of the entropy deficit, precisely the same formula to within a factor of 2. This factor of 2 is interesting. I'm not going to go into it here because, first of all, I don't fully understand it. But to within a factor of 2, the matrix model entropy with the idea that being motivated by matrix theory, that entropy has the same form as the entropy from the general relativity calculation. I don't think that's an accident. I think that's telling us something. It's telling us that at least in 4 dimensions, this calculation here is a 4-dimensional calculation. It will not work in other dimensions. Something else presumably works. I won't try to get into it here. I don't know what it is. And the suggestion is that at least in 4 dimensions, the fundamental holographic degrees of freedom are matrix degrees of freedom. That is not totally surprising, of course. Okay, let's try something a little more ambitious. How am I doing for time? Oh, I'm all right. Are you still there? Is everybody still there?
Yes, actually, there is a question from Edward Witten.
Okay. Please ask.
My question is the following, actually.
Hello, Edward.
Yeah, hi, Lenny. So the black hole and the de Sitter horizons, I assume, have different temperatures.
They do. So this is not right. So this is not, strictly speaking, thermal equilibrium. This is not in thermal equilibrium.
Well, the entropy, the matrix entropy must depend on the temperature. And since the temperatures here are quite different, it seems that's not just going to be factor 2, it should be a large factor.
I don't think that's right. I think I don't think that's right. I think the okay, let me put it this way. The temperature of a black hole, or the temperature of, it depends on what units you're using. If I'm working in Rindley units, then the entropy is just 1 per degree of freedom. The temperature is just 1 over 2 pi universally.
Mhm.
So I would say all horizons in that sense have the same temperature.
I see.
Okay?
Maybe. Okay, thanks.
Good. Okay. We can get back to it in our communication. I'm waiting for you to answer my my letter. Anyway.
Okay.
Good. Okay. Where am I? Okay, let's go to large black holes now. Black holes whose entropy is a finite fraction of the de Sitter entropy. This is a separate calculation. They're related. They're not completely unrelated, the small black holes and the large black holes. But I want to actually try to do the same calculation for all ratios, not just small ratios of little s to big S. For that, we have to go back and we have to study this issue of where the horizons are in more detail. So we start with the emblackening factor. We multiply it by little r. I'm not very good at mathematics, but most I can do is to multiply, to do a little bit of algebra, multiply by r to notice that this thing is a cubic polynomial. And we want to set this cubic polynomial to 0 to define the horizons. It has 3 roots. Let's forget the 2mg for a minute and look at r minus r cubed over r squared. That's a cubic polynomial, which goes to the origin here. It looks like this. And now let's add in the 2mg. We can put the 2mg on the other side of the equation. Here's 2mg. This distance is 2mg from the horizontal axis. And we see there are 3 roots. One of the roots is negative and doesn't have any physical meaning as a horizon. The other 2 roots are, here's the cosmic horizon. No, sorry, here's the cosmic horizon, the bigger one, and here's the black hole horizon, the smaller one. As 2mg gets smaller, the black hole horizon shrinks, the cosmic horizon grows, and right at a particular value of the mass, right? Here it is, right up here. The 2 solutions merge and form what is called a Norrii geometry, sometimes called a Norrii black hole, but it isn't a black hole. I'm not going to dwell on it here. That's the Norrii solution right at the top here. And that's in a sense, that's the largest black hole. I said it's not a black hole. Okay, it's the limit of black holes. It's the largest black hole that you can put in the de Sitter space. It has an entropy which is 1/3 of S naught right at this point here. Okay, let's define the following variable. Call it x. X is r plus minus r minus. Oh, incidentally, I'm going to continue these formulas to the point where r plus can be less than r minus. What does that mean? That just means, I'll tell you what it means later. It means that the cosmic horizon and the black hole horizon have interchanged their roles. I'm going to allow myself to continue the variables through values where the cosmic horizon is smaller than the. It's just a reflection about this point here. Okay, so define x to be r minus minus r plus. It's negative for a small black hole, and normalize it so that this is dimensionless. This also is equal, since in 4 dimensions, the radius of the horizon of a black hole, or the radius of the horizon of the de Sitter space, is proportional to the square root of the entropy. This is also the square root of the entropy of the black hole minus the cosmic horizon entropy divided by r, which is the square root of the de Sitter entropy itself. Keep that formula in mind. I know it's hard to keep things in mind, but keep that formula in mind. That's the definition of x. It can be written in terms of r's, or it can be written in terms of entropies. And it varies between -1 and 1. At the 2 ends, one or the other of the horizons are small and the other horizon is big. At one end, the black hole has shrunk to 0 and the cosmic horizon is big. At the other end, the cosmic horizon has shrunk to 0 and the black hole is big. Okay, now you can do a calculation. It took me a little while to do. It turned out to be easier than I thought, but the calculations are always easy after you've done them. But you can calculate the entropy deficit as a function of x. And it turns out to have a simple form, the entropy deficit, a very simple form, which very much surprised me. Delta S is equal to its value at x equals 0. And I'll call that the entropy deficit of the Norrii solution. The Norrii solution is right at x equals 0, right up here, times 1 minus x squared. Very simple formula. The simplicity of which I don't, when I say the simplicity, I mean, when I say it's calculated, this is a gravity calculation. This is a pure gravity calculation, calculating the entropies from areas of gravity solutions. This formula I want you to keep in mind again. And the other thing to know is that delta Sn right at the Nari solution here is a third of the entropy of the de Sitter space. Okay, we're going to do a matrix calculation of the same thing in a minute, but let's just talk about an interesting physical phenomenon. This is not one that we're likely to see tomorrow in our, even if our space was just de Sitter space. It is extremely unlikely, but here's the phenomenon. Let's begin with this picture here. We start at this end here. This end here is a very, very tiny black hole, maybe no black hole, a very tiny black hole, let's say, and a large de Sitter space. Energy flows from the cosmic horizon into the black hole. Now that violates the second law of thermodynamics, and therefore it's improbable, but not impossible. Energy flows accidentally from the cosmic horizon to the black hole, and thereby increases the mass of the black hole, decreases the radius of the cosmic horizon, until you get to the Nari point, where the two horizons are exactly the same size. And then if it keeps going, by accident, by simple fluctuation, the original cosmic horizon will shrink and the black hole will expand. The black hole will become the cosmic horizon. The cosmic horizon will become the black hole. So here's what this would look like to an observer. We start out with the de Sitter space with its cosmic horizon surrounding us. There's a small black hole at the center. It may have nucleated by fluctuation, but let's suppose we start with a small black hole near the center of the de Sitter space. Our observer is sitting somewhere between the two horizons and observing the black hole. If he turns around, he will see the cosmic horizon. Actually, he can see the cosmic horizon. Well, all right. He can look this way and see the cosmic horizon. He can look this way and see the black hole. All right, let's draw that. Let's draw that in a kind of embedding diagram. Here is the cosmic patch. Sorry, here is the static patch, but with the extra black hole at t equals 0. The observer is looking toward the black hole. Here is the cosmic horizon. Oops, sorry. Here is the cosmic horizon, and here is the black hole horizon. He's looking at the black hole. Energy begins to flow by accident, by fluctuation. It flows from cosmic horizon to black hole. The cosmic horizon shrinks. The black hole horizon expands. Eventually, the two horizons have the same size. They don't come together. They don't merge, but they have the same size. And the observer is stuck between them, seeing something symmetric on both sides. If it keeps going, Snoopy here will see the original black hole horizon expand and the cosmic horizon shrink and perhaps eventually disappear. He will see what I like to call the de Sitter space turning itself inside out. That's a crazy thing to see. You are not likely to see it. How improbable is it? In order for it to happen, we have to go through the Nari configuration. If you remember, the entropy deficit, let's go back. Let's see if we can find it. The entropy deficit of the Nari solution is 1/3 of the entropy of the de Sitter space. And so the probability for this to happen is e to the minus S0 over 3. S0, what is S0 in our universe? S0 is 10 to the 120 or something like that. So this is a mighty small number. But the point is, this is not something I am predicting we will see. It's a probe. Knowing these kind of things are probes into the fundamental degrees of freedom, and that's the purpose of them. Okay, how does matrix theory deal with the same problem? Again, here is the matrix type of configurations that I've been assuming describe two separated systems. We can study them as a function of m and n minus m. And in fact, the analog of the Norrie solution would just be block diagonals that split the big matrix in two. Equal entropy for the fluctuation and equal entropy for the cosmic horizon. So the analog of the let's see if I have here it is. The analog of the Norrie configuration in the matrix theory would simply be a pair of blocks, half the size of the original, with everything else being unexcited. What is the entropy deficit? It's just the number of constraints. It's m times n minus m. For the Norrie solution, m and n minus m are equal, but let's leave it open. Let's not go to Norrie. It's m times n minus m. That's the entropy deficit. That's just the area. Let's go back a step. That's the number of constrained degrees of freedom. That's the number of constrained degrees of freedom times the entropy per degree of freedom. And now let's define the variable x again. If you remember, x was the square root of s minus s plus divided by square root of s naught. This was r minus r plus over capital R. And the square roots of the entropies of the blocks are just the entropies of the blocks are proportional to the number of elements. The square root of the entropy is the linear size of a block. Whoops. And so x is nothing but m, that's square root of s minus, square root of s plus, and minus m divided by n, and here it is. This is x. And now we can go, I'm not going to do, it's a little bit of algebra. Here is delta s, here is x. You can do a little bit of plugging in, and you will find that delta s is equal to the entropy deficit of the Norrie solution times the same 1 minus x squared. Same formula that we had from the gravity calculation. There is a difference. In this case, the entropy deficit at the symmetry point happens not to be S naught over 3, it happens to be S naught over 2. What that difference in numerical value means, and if it has any particular important meaning, I don't know. Okay, I'm a little reluctant to go on to another subject now because it is late. So let me ask if there are any questions. It is late. It's 48, we're 10 minutes away from the end. If there are any questions,
Please.
ask them now. No questions. Okay. Yeah.
I have a question.
Yes.
If you say that the degrees of freedom are described by a matrix model,
That's in 4 dimensions. In 4 dimensions.
Yeah. Right. Do you have any guess as to what would be the actual dynamics, the Lagrangian?
No.
Okay.
No. That's right. Exactly no. The answer is I don't know what the dynamics is, and I'm not even going to try to guess. This is, as I said, I'm not trying to build a theory at this point. I'm simply trying to use hints coming from gravity calculations and see what they suggest. And at the moment, I think I don't nearly understand enough to guess any dynamics. the things that I've told you are much more kinematic than they are dynamic. And I realize that doesn't answer the question you wanted to ask, which was what is the dynamics? But it's an attempt to ask you a question, whether do I know what the dynamics is? The answer is no.
Yeah, thanks. I guess that's the $1 million question, right? So,
Well, yes. It's certainly an important question. I think it's an extremely hard question because the constraints coming from saying that the different static patches are all equivalent to each other. This is a symmetry constraint. If you like, it's the OD1 symmetry of de Sitter space. That is extremely hard to implement in this kind of holographic theory. And I personally feel very far from knowing how to actually build a model. So I'm telling you what I know and trying not to tell you more than I know. How much time do we actually have?
About 10 minutes. 10 minutes.
10 minutes.
Mm-hmm.
Well, there's not enough time to go through another subject. There were 2 other subjects I was going to talk about.
Of course, you can use 15 minutes. It's not necessary
No,
to finish
all right,
exactly in 1 hour. Yes.
Good. I will start. As far as I get, you can always go back to the paper on the subject and see what you can learn. And I'll start, and you just feel perfectly free to say you've used up your time. Okay, so an important part of holography is, of course, entropy, yes, but entanglement entropy. And in anti-de Sitter space, we've learned through the work of Ryu, Takenagi, and Hubini and collaborators, we've learned a kind of calculus for studying entropy, entanglement entropy. And the question is there anything analogous in de Sitter space? So I'm going to suggest what that analogous theory of entanglement entropy is. But first, let me quickly remind you of the RT formulation, or the H and the HRT formulations. RT is Ryu Takenagi. HRT is Hubini Rangamani and Tagenaki. But I'll just remind you. Let's start with anti-de Sitter space. Here we're in anti-de Sitter space, and we would like to calculate the entanglement entropy of 2 pieces of the boundary. In other words, the field theoretic entanglement between 2 regions of the boundary field theory, A and B. On the left-hand side here, we're talking about vacuum ATS. And what is the rule? The rule is we find the surface in the bulk, which is homologous to either A or B. That simply means you can get it by deformation of A or B. Some smooth deformation. What's going on here? You start with A, you start deforming it, and you find the homologous surface. You could start with B, doesn't matter, and start deforming it and get the homologous surface, the entanglement surface, and then demand that you look for the minimal surface. And that is together with the usual factor, the area of that surface is the entropy, the entanglement entropy of A and B, with the usual factor of 4G. Another example of it would be the 2-sided eternal black hole. In the 2-sided eternal black hole, there are 2 copies of the boundary, one over here, one over here. And we can ask about the entanglement entropy of those 2. And again, we divide the boundary, which is naturally divided, into A and B, and look at the surfaces which space-like surfaces which interpolate between them, and then look for the minimal surface. Good. So A min is the minimal area of such a surface. We can think of it, we can draw a picture. Oh, let me see what I have here. Yeah, okay. So here's a picture, and this is the picture of the two-sided black hole. And let's take a surface between a space-like surface anchored at the two ends here. There it is. And let's look along this surface for the minimal area. The minimal area will occur somewhere in here. I don't know exactly where it is. And natural to identify that minimal area with the entanglement entropy of both sides. But where should we put this surface? And the rule is to look for the minimal area of the cut of the surface and then maximize it over where you put the surface. The answer is to put the surface right through the bifurcate horizon. And the reason is because the area of spheres increases as you move down in de Sitter space and anti-de Sitter space. So this is the HRT formula. The max min area along any surface sigma which connects the two sides. I'm not going to try to be more exact than that because I want to jump on to de Sitter space. In particular, I want to think about the entanglement entropy between the left side and the right side, between the pode horizon and the antipode horizon. And so let's try the following formulation. Remember now that the holographic degrees of freedom are at the horizons and not at the boundaries. So here's a first proposal. Divide the generalized horizon, that means the sum of all the horizons in the problem, into two subsets. And now I'm thinking of the left subset and the right subset, the left horizon and the right horizon. And try out the following simple-minded version. The minimum area is the area, forget max min here, just min, of surfaces homologous to either subset. And then take that to be proportional to the entanglement entropy of the two sides. Now that won't work, and here's the reason. Here we have our two horizons, the two sets of holographic degrees of freedom. Here is a surface that's homologous to, for example, this horizon over here. It can be gotten by deforming or just moving it. And eventually, quite clearly, you can shrink it to zero. If that was the right formulation, just look for the minimal homologous surface, it would say that the entanglement entropy of the two sides is zero. And that's, of course, not what we expect. Let's see what all right, so here is the formulation, which I think is the right formulation, roughly. And we do not anchor the surfaces on the pode and the antipode. We anchor the surfaces on the place where the degrees of freedom lie. Anchor the surfaces on the two stretched horizons. And now take space-like surfaces anchored at those 2 points, okay, and look for the max-min surface homologous to either side, but with the specification that that surface lies between the two subsets. In other words, that it lies in here and not out here. We'll see why that makes sense in a moment, but we take the surface lying between the two sets of degrees of freedom and look for the max-min surface in here. Let's see, and take that to be the entropy. I know I'm going fast and some of you may be lost, but I'm doing the best I can. Okay, where is that surface? Where is that surface? Now, in anti-de Sitter space, as you move inward, the size of a local two-sphere decreases. But in de Sitter space, as you move in, the size of a local two-sphere increases. So, as you move away from the anchoring points here, the size of the local two-sphere always increases, and therefore, for any such surface, the minimal two-sphere occurs at the anchoring points. Of course, if you go past the anchoring points, you can shrink it to zero. But the rule that I'm proposing is that you should look at the surface between the anchoring points. In that case, the minimal surface associated with any sigma will be at the horizon itself. Here's another picture of the same thing. This is a space-like cut through here. A space-like cut through here. Here's the pole over here. Here's the antipode. And the reason for the bulge here is the left horizon, here's the right horizon. The reason for the bulge is that when you move past the horizon, the area of a two-sphere always increases because it's de Sitter space. In another language, the de Sitter space is always a Python's lunch. So there's a bulge in here. And now our rule is to look between the two horizons for the sphere of minimal surface area, and that occurs right adjacent to the horizon. It's degenerate. There's one at each end here. And that, of course, has the area of the horizon. And so you get the right answer, namely the horizon area over 4G. The picture that I like best for the Ryu-Takayanagi formulation is the so-called bit thread picture. Okay, I have a few more minutes, and so I'll tell you what the bit thread picture is. This bit thread picture is due to Matt Hedrick and Mike Friedman. And I think it really does capture something important about the Ryu-Takayanagi formula that maybe the original formulation doesn't capture, but it is a matter of taste. Here's the rule. You take bit threads. We're now asking about the entanglement between two sets of degrees of freedom, this one and that one. You start bit threads out along one of the degrees of freedom. Here are the bit threads. Bit threads are just threads, but they have a thickness. They have an intrinsic thickness, and the intrinsic thickness is Planckian. So they're not quite bit threads, they're bit ropes. And the bit ropes go from one set of degrees of freedom to the other. Each one has a Planckian thickness, and the entanglement entropy between the two sides is simply the maximal number of bit threads that you can squeeze through from one side to the other. There will typically be a bottleneck. The bottleneck will occur on the smallest surface, and the surface of smallest area. For example, if this went inward like this, there might be a smallest area here, and the maximal number of threads that you could send through would be determined by the smallest area. But in this de Sitter space setup, the bottleneck actually occurs at the anchoring points itself. And so the maximal number of threads that you can send through, and incidentally, in the bit picture, it's very natural to ask what goes on between the two surfaces and not, there's no way to go from here and then come out over here for a bit thread. So we are talking about the region between the two. Okay, the bottleneck is at the horizon itself, and what it tells you is that the entanglement entropy between the two sides is indeed just the horizon area in Planck units. Let's do the same thing for the problem of the Schwarzschild de Sitter solution, which, if you remember, has cosmic horizons, two of them, one for one static patch, one for the opposite static patch, and it has two black holes, and the two black holes are connected by an Einstein-Rosen bridge, or in other words, just saying that this horizon and this horizon are identified. What is the maximum number of bit threads that you can send from the union of this horizon with that one, that's the left side, that's the pod side, to the union of the horizons on the right side, the antipode side? And the answer, with a little bit of thought, we'll say the maximum number of bit threads you can send through is determined by sending bit threads directly from here to here. That will give you for the same reason, the bottleneck is at the horizons, and the answer will be the cosmic horizon area over here. But you can also send bit threads from the black hole horizon over here through to the other side, through the Einstein-Rosen bridge, and that will add in the entanglement of the black holes. That, again, is the right and expected answer, that the total entanglement entropy is the entanglement of the cosmic horizons and plus the entanglement of the black holes. I think I will stop at that point. Going on beyond that point would take us into technical things. The message here is that there is a proposal, in any case, for a calculus of entanglement entropy in de Sitter space. It has not been well tested, certainly not as well tested as the Ryu-Takeyanagi formula. And I will leave it at that. If I had another hour, I would tell you one more thing. I would tell you about a proposal for a particular model, not for four-dimensional de Sitter space, but I actually think it's three-dimensional de Sitter space based on the SYK model. This is even less well tested, but I don't have time for it, so we'll have to leave that for another time. Thank you.
Okay, thank you very much,
Thank you.
Lenny, for your wonderful talk. Okay, any questions, please? Okay, Shravan, please.
Hi, Len. Thanks for the nice talk. Actually, I have two questions. One is about, you started with you want to preserve unitarity. So how you are preserving unitarity with this connecting the antipodes with the Einstein-Rosen bridge? Are you preserving or not?
Well, the assumption is the same as the assumption in for the same reason. I'm not sure I quite understand the question. The assumption is that the pode and the antipode separately are described by their own quantum mechanics, and the quantum mechanics is unitary Hamiltonian quantum mechanics that leaves room for the two sides to be entangled, but not to be interacting with each other. That's exactly the same assumption you make in black holes. The interior and the exterior of the black hole are in some sense entangled. Or let's take the two-sided black hole. The two-sided black hole are entangled but not interacting.
Oh, okay. And another question is, well, I mean, it's been a long-standing problem for de Sitter space. We cannot define S matrix.
Right.
Right. So, I mean, do you have some resolution for that?
Yeah. No. To put it another way, there is no asymptotic boundary. Now, there are asymptotically space-like boundaries. Those are the infinite future and the infinite past. And a holographic, I wouldn't call it a holographic description. Descriptions on space-like boundaries are not standard quantum mechanics, but that is what the people who try to think about the DSCFT formulation try to focus on those space-like boundaries and place the holographic degrees of freedom there. Is that a valuable way to try to formulate things? I suspect it is, but I think it's mainly valuable in thinking about inflation and the transition from inflation to where a future observer can see everything in the past, but in eternal de Sitter space, I'm not sure what the logical status of space-like surfaces, which asymptotic late space-like surfaces are that nobody can see. The thing that an observer can see is a static patch. And so what I mean by holography is what I meant a long time ago, is a description on a time-like boundary, on a boundary of space. And so I would not include DSCFT to be holographic in that sense. No, I forgot what the question was.
Okay.
Why did I get into that? I don't remember what the question was.
No, I'm trying to recall the color. No. Okay, it's okay. I think I'm a bit lost.
Good.
Maybe we can pass to another.
Okay. Misha Kramsov, please ask your question.
Okay. Hello. Thanks for the talk. Can you please comment a few words, maybe about what kind of observables would you have in mind to test the proposal of de Sitter SYK duality at the double scaled limit?
Yeah. God, my habit is to write everything I know in a paper. And then people ask you questions, and the only thing I can say is I don't know. If I would have known, I would have put it in the paper. The paper was again an attempt to use some circumstantial evidence to make a guess about some formulation of de Sitter space, and not. But it's a good question. I think the question is, how can you confirm that the geometry of the double-scaled limit is the geometry of de Sitter space? And I honestly don't have a strong proposal for that. The two things that I know is there's a fit with the behavior of scrambling for degrees of freedom located at the horizon. And the other thing is a fit with the strange way that complexity behaves, or let's call it holographic complexity behaves in de Sitter space. Those are the pieces of circumstantial evidence, and it's really the only thing that I know. I put it out there in hopes that people who really understand SYK would be able to figure out what the bulk geometry looks like, but I don't know how to do that.
Yeah, so there is also some symmetry argument by Herman Verlinde. I think you referred to that in your paper as well.
That's right. And I honestly have not been able to penetrate that. I have a problem reading papers. Oh, this wasn't even a paper. This was a lecture with when Herman sent me the slides from the lecture. Without having Herman there to explain it, it was a little bit obscure. So
he also has a comment in one of his papers about this as well.
He does. So, okay. He didn't tell me that, but
I've actually sent a link to you earlier by email.
Oh, excellent! Good. He told me that he and his colleague are writing a paper, so I'm looking forward to seeing. There is a point that was something of the inspiration for this thought. The question was not about the double-scaled limit, but the question about why de Sitter space, why go to a high temperature. Incidentally, infinite temperature in SYK is not very hot. Infinite temperature won't burn you. It's really more like finite temperature in an ordinary system. The point being, there's an upper bound on the energy spectrum, and so even when you go to infinite temperature, you're not going to very high energy, or you're not going to infinite energy. Anyway, here's the. This is what the JT gravity Penrose diagram looks like. If you've seen it before, you'll recognize it. If not, you won't. Then the interesting thing, or one of the interesting things, is that in representing SYK, the boundary of the geometry of the Penrose diagram gets pulled in a little bit, depending on the temperature. If the temperature is very low, the boundary gets pulled in a very, very little bit. And the higher the temperature is, the more it gets pulled in. The boundary, usually for SYK at very low temperatures, is imagined to be very far away from the horizon, with a long throat between left boundary and right boundary. And this long throat is the thing which has the SL2R symmetry, the two-dimensional anti-de Sitter geometry. And the whole business is deeply connected with the fact that this long throat has structure reminiscent of conformal geometry and so forth. What happens is you raise the temperature. As you raise the temperature, the boundaries move inward and eventually become practically indistinguishable from the horizons. That suggests that high temperature is the situation where the holographic degrees of freedom are represented as stretched horizon degrees of freedom. That high temperatures is the situation where degrees of freedom of the holographic description are near the horizon rather than far away at some boundary. That then leads to the problem. If the degrees of freedom are located on these boundaries, maybe in some approximation, the Schwarzian degrees of freedom probably are. The problem becomes reconstructing what's in here. What's reconstructed in here would be the pole and the neighborhood of the pole. Actually, the pole is usually on this side, the antipode and the neighborhood of the antipode. So reconstructing from the boundary degrees of freedom over here, perhaps just in some way of some extrapolation away from these boundaries here, reconstructing what's going on out here becomes the problem of reconstruction of the pode and the exterior region of the de Sitter space. And this picture was to some extent inspiration for thinking that SYK at high temperatures would be involved in a de Sitter space construction. The other element was not only high temperatures, but high Q, little q. And that's a separate issue. And you can read about it in the paper. But as I said, again, two pieces of circumstantial evidence, and that's it. The behavior of scrambling, hyperfast scrambling, and the behavior of complexity growth match expectations, I think, for the de Sitter space.
Yeah, that's interesting because for complexity growth, I would expect that at late times, the Liouville theory approximation and double-scaled limit breaks down. So for the SYK computation, I would have to extrapolate the large Q solution.
Yeah. Okay. Let me just say for the issue of the holographic complexity. Here's the de Sitter space. Now, what we'd like to do is, let's take the simple formulation of holographic complexity based on volume. The natural idea would be to take a surface anchored on the horizon at some time, t, and look for the maximal surface, connecting the two of them, and the volume of the maximal surface would be proportional to the complexity. Alternatively, hold on. We could try using the Wheeler-DeWitt patch and calculate the action of the Wheeler-DeWitt patch. In either case, at early times, we would get some finite answer. But as the time moves up, we eventually get to the point where the maximal surface, both the maximal surface and the Wheeler-DeWitt patch, intersect the future horizon here. The future infinity here. And the reason, why does the maximal surface want to go up so high? The answer is because in de Sitter space, the local two-sphere increases rapidly as you move up. And so to capitalize on that and looking for the maximal surface, you always push it up as far as possible. In anti-de Sitter space, the opposite is true. So you eventually hit this point here. Let's assume this gets regulated by something so that it's not truly infinite, just very large. Then after that, the maximal surfaces have very, very large volume. And they grow very, very rapidly. This is a feature of de Sitter space geometry, and it suggests you should look for a theory in which complexity growth is much, much more rapid. After a brief transient period, the complexity growth is much, much more rapid than it would be for a standard kind of quantum circuit. And that was the motivation for saying that Q should go as some power of n, for example, n to the 1/2, because when you have this kind of condition, that would lead to anomalously fast complexity growth. So as I said, this is all a lot of guessing. But it does come down to a fairly concrete guess that SYK in this double-scaled limit here, let's just put it this way, has more in common with de Sitter space than it does with a black hole. We will find out. Time will tell.
Can we guess a time scale of this transient period in terms of Q? How it scales with Q?
It's about the de Sitter radius.
No,
It's
but
short.
in terms of SYK Q, which is large, is it meant to scale with Q, or is it supposed to be finite?
Let's see. Good question. J, is it J, inverse J? Something. Yes, I think that's right.
Okay, so
I think.
so it's finite. Okay.
Yeah, it's finite. It's finite, small. Yeah. So that's right. So there's a small transient period. In terms of de Sitter space, it's basically the inverse temperature. But now we're talking about high temperature, not low temperature. I think in some ways it's better to say temperature of order 1. There's not much difference between temperature of order 1 and infinite temperature in SYK. Very little difference.
Yeah. Okay, thanks.
Okay. More questions, please? Okay, maybe I will ask questions. What happens then instead of de Sitter, you consider Reisner-Nordstrom de Sitter, for example, or something else? What is your expectation?
Okay, that's interesting. Adam Brown and I were just talking about it the other day, and I can't remember. He's a great expert at that, and I can't remember what he said. Right, it opens up a whole new. You're right to ask the question, and I can't remember what I know about it, what I knew about it. But it opens up another axis of directions to explore fluctuations in, namely fluctuations which lead to charged black holes on each side. And I think it creates new data, but I can't remember exactly what it is. It certainly doesn't conflict with the old data, and I don't think it changes the picture very much, but I think it would give you a whole new function, a whole new function, not just a function of the masses of the black holes, but a function of the charges to try to explore and to ask what it says about these microscopic degrees of freedom. So the answer is I don't know.
Okay, thank you.
There are lots and lots of things that can be explored.
Okay, thank you. More questions, please?
I'm sorry to say almost for every question I don't know, but I don't know. So
Okay. Okay.
I can ask a question.
Yes, please.
Earlier in the talk, Ed Witten pointed out that, if you have a black hole horizon and a cosmic horizon, there are different temperatures.
Yes.
So, and I mean, you gave an argument for why you think that the bulk geometry is in.
Yeah, there's always 1 degree of freedom per unit area,
even if
whatever the temperature is.
Yeah, sure. So, no, I mean, even if one does away with the assumption of thermal equilibrium, is it still possible for your reasoning to go through in some way?
Well, I don't think I used really. The formula that I used, let's see. A black hole in de Sitter space is certainly is as much in thermal equilibrium with its environment as a black hole in flat space. A black hole in flat space is not strictly in thermal equilibrium. If it were thermal equilibrium, it wouldn't evaporate. But nobody hesitates to use the Bekenstein formula for the entropy of a black hole in flat space. Why do we get, and nobody would hesitate too much to think of the black hole in flat space as being approximately in thermal equilibrium. Why are we allowed to do that? Well, the reason is because the evaporation is so slow that there's plenty of time for the system to equilibrate locally. It's not, strictly speaking, in equilibrium with the environment. The environment in flat space is 0 temperature far away. The black hole is finite temperature, and so it's out of equilibrium. But that never stops us from using equilibrium physics to study the black hole, because the black hole evaporates so slowly that it's not very important to the internal dynamics of the black hole that it's out of equilibrium. I think exactly the same thing is true in de Sitter space. And in calculating the entropy, for example, of a black hole, I don't think that being out of equilibrium with its environment is important.
Okay, I mean, I would suspect that when one is looking at black holes which are very small, which is the limit that you took.
Well, small now I mean small compared with the cosmic horizon.
Oh, I see. Okay.
A billion solar mass black hole is small.
Yes, definitely.
Right.
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 Okay. More questions, please? Okay. If there is no more questions, let's Thanks, Lenny, once again.
Okay,
And-
I have a question.
Oh, please, please.
Where is this seminar taking place anyway?
Sorry?
Where are you people?
Where all of us are virtual. I'm personally
I know.
in Moscow.
Where are you?
Yeah, I'm here
Which is where?
in Moscow.
Ah, okay.
In Moscow.
I wasn't sure if you're in Moscow, Leningrad, or where, but
Okay, because
it's been a while since I've been in
said
Moscow.
that you haven't, if you would have 2 hours, you can tell us more. Maybe we can use these words to invite you to give a seminar, next your seminar
Right,
sometime. Okay?
Well, okay.
Okay,
Yeah.
because it was very, 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 very instructive, and
Thank you for helping me wake up this morning.
Oh, I'm very sorry. I cannot send you a cup of coffee.
Yeah. Okay. Good.
But, yes.
Okay.
Thank you very much.
Thank you.
Thank you.
Thank
Bye-bye
you
now.
for a great
Bye-bye,
talk.
everybody.